The last time we looked at the way to measure speed, and in many different speeds there are, the different definitions you have of speeds.
But also when measuring altitude, there are many things to account for. We measure altitude using the static pressure. However, it is important to realize that a pressure difference is actually used to measure the altitude. And this means what the reference pressure is important to the outcome of the altitude calculation. Well, if we use the sea level pressure for that given day, we will get our true altitude relative to the sea level. However, if we use the standard atmosphere calculations, we will only get it relative to 1013.25 hectopascal. So this means that there is a difference. And how do we deal with this difference? How do we deal with the weather influence on pressure changes? Well, here we've indicated the way to deal with this. We see that the altitude, the word altitude in aeronautics always refers to the sea level, relative to the sea level. So the weather of that day, the pressure at sea level of that day, influences the value for altitude. If you hear an altitude given in flight levels, this uses a standard reference of 1013.25 hectopascal, the value we know from the standard atmosphere. And the word height, for decision height or height in general, always refers to the altitude above an airport. So the pressure at the airport is important then. There are also abbreviations related to this usage of speeds, and for instance the QNH is used when you use the pressure relative to sea level. QNE, hardly ever heard anymore, is the flight level altitude, and QFE is the field elevation measure, or in other words, the height. Normally in aeronautics, most of the time QNH and flight levels are used. But if both of them are used, when do you use which? Well, this brings up the issue of the transition altitude. So how do you know when to use the feet, the altitude, or the flight levels? For this, we use the transition altitude. The transition altitude is the altitude under which you have to use the feet, so relative to sea level, and above which we use the flight levels. Flight levels are, by the way, expressed in 100 feet. So flight level 085 or flight level 85 refers to 8,500 feet above the pressure of sea level in the standard atmosphere, so 1013.25 hectopascal. While if the altitude is expressed in feet, 8,500 feet, this means, as a reference, the sea level pressure of that day, so the weather information, is used to calculate this altitude. During takeoff and landing, the altitude is the most important altitude, and that's why it's used in this phase. While if you are above the transition altitude, you might be en route, and you don't want to check the weather on every position en route, change it all the time, and we also want to make sure that two aircraft that meet each other over the ocean will still miss each other if they're flying at different altitudes. And this is ensured by using the flight levels above this transition altitude, because both of them will then have used the same reference, the standard pressure. And this is why we have this transition altitude, which is locally defined. It might be as low as 3,000 feet in Europe. It could be as high as 18,000 feet in the United States. You may have seen an effect of this altitude and the QNH, or the pressure at sea level, that varies when you fly in a general aviation aircraft. Because when you start, you have to adjust your altimeter. If you take a slightly closer look at the altimeter, you can see that there is a small knob here on the side of the altimeter with which you can adjust a value which is shown in this display, which is the reference pressure. And this, using the weather information of that day, is set to the sea level pressure for that day. And this also means that when you are at the airport, the altimeter will often not show 0 when you are at this airport, but it will show the airport altitude. And this is something to take into account. So this is what we discuss for now about speed and altitude. But if we move from the primary flight display to the navigation display, we will see there's also might be some surprising effects also in what we show there. Let's start off with how we navigate in an aircraft. If you fly from Stockholm to Los Angeles, you might think, looking at the map, that this is the shortest route, the blue line, the straight line. But in fact, you will see that aircraft flying from Stockholm to Los Angeles do actually fly this route. Why is this? Well, the main reason for this is that it is much shorter. And this is an effect of the projection that is used in most maps, which means that on the top side of this map, there's a distance which is very small, while on the lower side, the distance is much larger. It's easier to imagine if you look at a globe. If you take a globe yourself and you use a little wire, you move it from one location to the other, then you really pull the rope, you will find the shortest distance. And this distance is called the Great Circle, because it's actually a circle with the center of the Earth as the center of the circle. And this is the shortest route, the Great Circle, and this is what aircraft fly. And that's also when you fly from Amsterdam to the United States, you will often pass the lower side of Greenland. But also if you look at the actual heading, which by the way varies when you fly this Great Circle, it's not the same heading all the time, but also you will see that the heading that we see on the navigation display is not the true heading. There are a number of mistakes. First of all, to measure the heading, we use the magnetic field of the Earth. And the magnetic north of the Earth is not the same as the true north. This means that there is already a slight change in what we measure and what it really is. And if we look what the difference is between the true north and the magnetic north, we call this the variation, the magnetic variation. And this is not even the same everywhere around Earth, because there are local influences for different areas, and there is a temporal influence. The magnetic North Pole is not a steady position, but it depends on the convection in the Earth core. And this convection changes, these patterns change, and this means that the field of the Earth changes over time. We see an animation here which shows how the variation changes over time. Every year, it's not per day, but every year it is updated, so you have the latest information, and then for a year we use the same variation. And also the amount of iron in the core determines local variations, and all these patterns and this iron in the crust means that there are different variations in different locations. And of course, just like with the altimeter, there is an instrument error. The instrument error is called the deviation. So summarizing all of this, we measure a heading with the compass. We first have to correct for the instrument error, and this is called the deviation, to find the real magnetic heading. And then, again, we have to correlate, we have to add the variation. We use to the east as a positive number to get the true heading. And then, if we want to take into account the effect of wind, we also have to use the displacement of the aircraft by the wind to find in which direction we're really traveling, and this is called the track angle. So the heading is associated with the airspeed, while the track angle is associated with the ground speed. And this brings everything together from heading to speed where which we started. I hope this gives an overview of some of the basic difference in true parameters and the parameters that are shown in the cockpit. The magnetic heading, by the way, is also used for the runway heading or for beacons, and this needs to be updated every year. So you may have noticed that sometimes runway names in terms of numbers have changed. This is an effect of the changing variation.